everyone. My name is John Craig Miller. I will be your presenter today, and I'm going to talk today about parallel and high-performance computing. This webinar is a follow-up from one that I did a few months back, and this one includes some more material that I didn't have available to me back then because it was still under development. So today I'm going to spend about half hour, and I'm going to show you some of the newer stuff we're working on and what we have completed in the high-performance computing arena with PSCAD. Now, just to recap, we've been working for several years now on high-performance computing and making simulations in PSCAD run faster. And we've used a couple of techniques for breaking systems apart and parallelizing systems across multiple CPUs and distributed computing. So our background is that we have available now hardware which is commonly used in offices and workplaces that have many CPUs built into it. This wasn't available until about 2005, 2006, and so there was not a strong motivation for parallel computing for PSCAD for desktops. Now that this is commonly available, this is a strong motivator for making simulations run faster. So what I'm going to show today is some of the motivation, some of the experimental developments, and some of our targets. It says future targets now, but this is from the previous one. We're going to show where our current targets are at. There are quite a few slides, so I'll skip down a few, but I'll get to the more relevant material as I go down. So just to recap, we've been striving for methods to speed up simulations and computation time. One way to do that is writing better algorithms, using better mathematical techniques. And the other way is to use hardware-based methods that can accelerate the computations. Historically, much of the simulation has been compromised, and we've had to live with more of a coarse-grained analysis because we just don't have the time or the hardware available to do all the computations. This adds to some frustration, and the software just hasn't caught up with it yet. In the early years, we just had a single process. So we moved on to task parallelism and data parallelism, where we wanted to break the problem apart into two problem areas. The data parallelism is more of a batching kind of problem where you want to run a simulation, but you want to do it over a number of different criteria, and you want to run the different criteria in parallel on different CPUs. This I won't talk about today, but this is heavily used in PSCAD for parallel multiple run. What I'm going to focus more on today is one of the more challenging tasks, which is the task parallelism and the latest developments in the task parallelism. So we experimented by running several projects in parallel, and then we also experimented with exchanging data between projects using a master and slave method. And then we got single projects to run multiple simulations at the same time, but under different criteria. So this is the data parallel that I was explaining. Then more recently, we started to interconnect between the individual simulations extra communication lines. The idea being is that now that the individual simulations could talk to one another, they could work cooperatively into a single larger simulation. We also connected across these larger cooperative simulations across a network, and that network is illustrated by the dashed line. The interesting part is once we go outside of the computing platform and we have to travel across the wire to another computer, This is where our communications problem becomes most evident, because it takes a lot more time to trade information across the wire than it does within the computer itself. We use distributed computing to try and deploy across a grid, and these had a number of benefits and a number of weaknesses. But the most important thing that we learned in the process of these experiments is that communications was a critical aspect of the problem space if we want to run faster on hardware. So we want to really run simulations with greater fidelity in more or less the same time, or less if possible. In order to do this, we need parallel computing capabilities. We need operating systems that interfere less with the actual task of solving the problem. We need cores, many cores on a single CPU with as high a clock speed as possible. Typical desktops these days can have 4 to 6 cores per CPU with 1 or 2 slots. So 4 to 6 core computers or 2 slot 12 core computers are not really that difficult to acquire. Blade computers can provide many more cores. However, they typically have a slower clock speed, so there is some penalty to be incurred when using a blade type computer. So with the task parallel, the fundamental is the high frequency of communication. Essentially very, very low latency is required. We're not transferring a lot of information between the individual processes. They're just very small amounts of data, but we have to transfer them very often and very quickly. So the communication backplane we'd used in the past was a standard TCP/IP network type. And we discovered relatively high communication latency across the LAN for sure, and fairly low across local host, but still it was not so efficient. So if we look back at our methodology, what we wanted to do was just create a system whereby we could scale up without changing the type of simulation too much, but we want to scale up so that we add more and more CPUs to the problem and more communication pathways. So that way all we're measuring is what does it take to communicate between these different simulations, not the balance of the simulation load. We want to eliminate that, so that's why we used identical systems in all cases. We want to make sure that each and every process is running the same amount of work each time, but we're scaling them up in order to build a larger aggregate system. So our early test was to just take 39 bus IEEE cases and tie them together with a fictitious transmission line. Now, as in the previous webinar, the decoupling point is the transmission line. This is a well-known technique that's been used for many years in real-time systems and other software implementations to break apart the subsystems such that they can be computed independently. All we're trying to do here is focus on how can we break these systems apart, put them on separate processors, and make sure that the communication between the two subsystems is as efficient and as fast as possible. So we ringed together a series of 39 bus cases, and we can continue to connect transmission lines between them in a ring pattern like you see here. The idea is each system represents a subsystem, and each subsystem is evenly balanced so that we know that the load is identical on each processor. So we could measure just the communications time. Also, it's very easy to scale up to more and more CPUs so that we can observe the pattern as we stress test the system larger and larger. In earlier tests on TCP, we found that as we use smaller systems like the 14 bus, the communication overhead was much greater than the actual execution time. So if you look at the first graph of the 14 bus system, you'll see that the execution time is much higher than the red line. Sorry, the execution time in total is much higher than the execution time of the solution on a single core. And that's simply because the communication overhead shown by the green line is just overwhelming the system. So this was an expected behavior that we saw, is that communication is just simply overwhelming any speed advantage we might get by splitting it across multiple CPUs. So the red line representing scaling the system on a single CPU shows that it's much faster when the systems are small. However, as we scale up, you can see the 39 bus, the lines start to come together. And so the right side graph, which shows the speed up, which in this case is actually a slow down, the curve changes. So as we increase up to 7 systems, it's slowed down. As we increase the size of each system, the slowdown is not so evident. Then as we make the systems larger, we find that there's a tipping point when we're using TCP at about 78 buses, where the speed in a single CPU is about the same as multiple CPUs. If we increase this further, we can see now we start to get the benefit of the acceleration, because while the communication is still the same, it doesn't grow with the size of the system. So as the scaling of the system increases, we start to see the benefits that we're looking for. And as we go to a 300 bus system, you can see that the scale of the system ensures that we get a linear speed up factor in the end. So what would a webinar be without a few formulas? So let's throw one in here. It's a fairly simple one, but the idea here is we just want to have some way of predicting what will our performance be based on these certain criteria. So we've created this formula here, which essentially measures how much time is it going to take to solve the entire simulation based on the number of times we break it and the amount of communication time and the amount of solution time. So the solution time, TSOL, and the communication time, TCOM, are integrated into this formula, which is based on the number of decoupled subnetworks and the number of connections. Now we know as we break the subnetworks apart, or we use more subnetworks, we have to connect the subnets together. So there's a certain limitation where Y has got to be at least the number of subnetworks minus 1, and at most it can be a much larger number. But we know that it's going to be a certain amount, and we know that the number of transmission lines that we're using for connecting the systems together is going to increase as well. So based on this formula, the communication times becomes a critical part of the total time it takes to solve the problem. If we can make the communication time, or the latency, as small as possible, that allows us to break the system up into much greater granularity. So the key to performance gain is smaller computation grains, but we want to make sure that our communication speed doesn't inhibit this. So our goal here is to figure out how can we make this as small as possible. So our approach was to apply better techniques for communication. We want to be able to have communication latencies that are at least as good as TCP on a single node, and certainly nowhere near the latencies that we see across nodes. But we want to be able to break up the system into as many pieces as possible. This means we just can't fit all the pieces onto a single compute node. This forces us to spread out across a network of multiple computing nodes. And if we want to have 20 or 30 or 40, it's more difficult to find computers that can carry that number of CPUs, and certainly at a high clock speed you won't find that. So we want to be able to spread the simulation across 4 computers or maybe more computers that have large numbers of cores per node. And then we can break systems into much larger and much smaller pieces of granularity, so we can handle much larger systems as well. So we make some assumptions. We need really fast communications, both localhost and interhost. Is it possible to break a large system into 100 smaller subsystems? But typically we only have 12 cores or less. We need multiple compute nodes. What if we applied supercomputing network hardware? What if we used high-end hardware that is typically used in supercomputing environments for clusters? Can we apply this on traditional desktop machines and use it with PSCAD? What we want to be able to do is we want to use parallel computing and achieve performance figures that we've never seen before in the offline type EMT tools. We want to be able to use standard TCP if high performance computing is not available, the hardware. If we don't have the fast hardware, we want to still be able to use the standard network. Further, what we want to do is we also want to be able to communicate using interprocess methods on a single node without going through the TCP method, the TCP stack. That way we can create much more efficient ways of trading information by just using memory. Now, to communicate across the hardware, what we've chosen to use is a well-known InfiniBand model for trading data across high-speed networks. Now, in our early tests, we used a large core computer, and this one in particular has 4 slots with 8 CPUs each, hyper-threaded to 64 logical cores. And what we did is we wanted to test how well it would work within a single computer with as many breaks as possible. Then, our more recent hardware, we've gone to as high-end desktop machine as we could find, which is Lenovo P900. It's a dual slot machine with 10 cores per slot, also hyper-threaded and running at 3.5 gigahertz. So as a single node, this is a very powerful machine, so it gives us a great opportunity to experiment with a shared memory model as well as operate across using high-speed networking. For the networking hardware, we use InfiniBand switch using some of the latest technology. I don't think it's the latest, but it is almost the latest. I think it's a 14 data rate model, and we use the networking cards plugged into the P900s. So we create an environment where we can use multiple computers like this and use the InfiniBand hardware to communicate small bits of information across the processes between the different computers. This is an early picture of initial setup and testing, and then this is later on where we now have 4 of these P900s, as you can see at the bottom there, connected together using the InfiniBand switch. But what we wanted to do is we wanted to get real measurements of what kind of performance gains we were getting. So we not only included the InfiniBand, but we included as well an Ethernet switch in between as well, so that we could compare side by side the same machines on TCP and InfiniBand at the same time. So this is our experimental test rig. In this case, we're showing 2 nodes, or 2 compute nodes, but we have 4. But this is all we need to show here. So we have the InfiniBand at the top, and then the Ethernet on the bottom, running in the same setup, so that we can compare them side by side. Now we know that the InfiniBand, the latency between the two, is much smaller than an Ethernet method. In addition to this, what we also did is implement a memory model where we can use inter-process communications between two processes, in this case two subsystems of the simulation, using shared memory. And what we did is we mimicked the same method used by the InfiniBand hardware, but we just did it in a software model so that the two look very similar to one another. In addition, and this may seem a little more computer science than engineering, but essentially what we did is instead of having several communication channels open, so in this case you see 3 buffers on one side and 3 buffers on the other side, this would represent, say, 2 subnetworks with 3 transmission lines in between. So we'd run the 3 transmission lines into a single communication channel and then demultiplex it on the other side to the other process. This reduces the number of communication channel between the individual processes. So the idea is to improve the efficiency. And we use a classical scatter-gather technique for collecting and then demultiplexing on the other side. So between the 2 processes, or the 2 subsystems, we have essentially a pipe. And the pipe has one direction passing messages one way and another direction passing messages the opposite direction. Because when we're simulating the transmission line, we actually have values being pulled out at both ends and pushed in at both ends. So the pipe is bidirectional. When we go across nodes, what we use is what's called remote direct memory access, or RDMA. It's basically a DMA, or a direct memory access method, that can work across nodes in a network. The advantage of this type of method is we can bypass the typical TCP method of transferring information and use this in favor. The difference is RDMA method over InfiniBand does not require any CPU cycles from the computer itself. It does all the work. The operating system doesn't have to do anything. The CPU doesn't have to do anything. The hardware itself takes care of all of the memory transfers and read and write operations. The result is we get much faster point-to-point speeds between nodes. If we look at simple examples here, if we use a transfer of 64 bytes, which is typical for our application because we don't use a lot of data. We use very small amounts of data between the subsystems on either side to transfer the values across the transmission line. So if we look at this, we can see InfiniBand is down under 1 microsecond, whereas even in localhost, the TCP is around 20 microseconds. PAX, which is our term for our inter-process communications using shared memory, is also in around the same speed as InfiniBand, very close. If we use a slightly larger size of transfer, 8 kilobytes, you can see the InfiniBand increases to 4.7 microseconds, and the PAX is at about 1 to 2 microseconds. The TCP remains unchanged. But if you go across machines, and if you look at the across machine times, you can see how much higher the TCP times are. And so this is really the big motivator for getting away from that type of method. How does it bypass? Well, if you look at the RDMA transfer map, you can see on the left side there's all this activity going on in the kernel, which is managing the transfer of information over TCP. This is the operating system, the TCP stacks, the drivers, everything that the operating system and the hardware has to do to work to get that message transferred across TCP. If we go to the right side where we have RDMA, this is completely empty because the kernel does nothing. It doesn't have to. The operating system doesn't have to do anything, neither does the CPU. It's all handled by the hardware, and in doing so, it's optimized for that kind of performance. So we get very low latencies. So, having described all that, this picture is one that I showed at the end of my last webinar, and what it's demonstrating here is how the whole system is pieced together. It's a fairly complex diagram, but what it shows here is 3 EMTDC subnetworks. So they're highlighted by the green boxes. And 2 computers, host 1 and host 2, which is shown by the large black rectangles. Then we show the communications method between the 3 EMTDCs across the different methods of communication. So we built something that we call the confab, which is a communication fabric. Its whole purpose is to slide in between EMTDC and all of the hardware and make it transparent to EMTDC and the processes how to talk to another process. So in doing so, it allows the confab to decide the best way to transfer information across. If the 2 EMTDCs are on the same host, we use a shared memory model. If the 2 EMTDCs are on different hosts, then we go through the InfiniBand and transfer through RDMA, which are the pink boxes. Now, if we don't have the InfiniBand, it can also use TCP, but to a lesser performance extent. So the confab is built to allow for 3 methods and to use those 3 methods transparently based on what is optimal for accelerating the simulation. So if we have a network of computers, we end up with a multi-node fabric that looks something like this. So if we have 2, 3, 4, in this case 6 machines working together, they act as a cluster, and the InfiniBand helps create that performance, and the confab decides how to communicate between the processors. So going back to how we split a network, if I say let's go out here, maybe I'll go out and we'll go to PSCAD itself. Let's have a look at PSCAD itself. Hopefully you can see this. Now, here's the case that I showed in the slide. So this is a very simple example benchmark case that's been used hundreds and hundreds of times to demonstrate things. This time I'm going to use it to essentially demonstrate the basic splitting of 2 subnetworks. This is a DC link that's connected by a line here, and we have a subnetwork on the left side and a subnetwork on the right side. To configure this to break, we use the line ends, and using the line ends, we can then control how we want to send the information. We can specify what is the name of the other project we want to send to, and we can also specify if we want to pass any control signals through. We can use sending and receiving dimensions. So not only can we transfer the electrical values, but we can also pass control values through the transmission line pipe. Since we don't have these subsystems operating in the same process anymore, there's no way we can share control signals. They have to be formally passed across the pipe. So if we go to the other case where we've split it, now we've taken the left side and we've created essentially the left side of the network here, including the line. Only one side includes the line because only one side does the simulation of the line. So by convention we call this essentially the server side because it includes the transmission line. It's just a terminology, but it basically means that one side is a server, one side is a client or a connecting to type approach. So this particular case split into two. If we look at the other side now, this is the client side here, which is connecting to. So this end of the line, transmission line end, is sending a control signal in and connecting to the other end of the transmission line. So you can see it's highlighted saying this is the BM1, but we're in the BM2 case, and in this case we're in the BM1 case. This one is the sending side, so it specifies the transmission line name. So the sending side doesn't need to specify what it's sending to, only the client needs to specify what it is connecting. This helps in configuration and avoids confusion. So if we run the single case, so we run all in one, and we get our graphs. Then if we run the two split, and I'll go over here, run the two split, I have to pair them up into a simulation set so that I can run them in pairs. And I run the set, and they connect and run. And so just like that, it's done. So that's the basic method. Now if I go back to here, and where was I? Alright, so we showed you that, splitting, and then the other side. And now what we do is we're going to do some benchmark testing. So what I have here is a number of cases, and the whole idea here is we need to push the boundaries and find out what are the limitations and what is the performance we can achieve. So we start with a super simple two subsystem model, as simple as we possibly can, because we want to stress test the communications. So we use a simple AC. We also use a mix of a wind turbine, wind farm, lumped wind farm model. We also use a mixed network, connecting two larger networks together. And then this case here, which is kind of interesting, this is a wind park. Now in the case of the wind park, instead of lumping the simulation or lumping the models for the wind turbines, we're actually simulating each wind turbine in full detail. And the wind turbine has built into it a full control system and back-to-back DC link. These are modeled in full detail, including all of the switching that goes on, so they're computationally intensive. So it makes a good example of how to take an individual part of the simulation and put it on a separate CPU. Now if we look at the numbers are all standardized to seconds and microseconds. Now all our simulations run in seconds, and all the simulations run for 1 million steps, because we want to make sure that we're benchmarking against apples to apples. So we're using 1 million communication steps. So for example, if we have a simulation running at 10 microseconds, we'll run the total simulation for 10 seconds. That makes 1 million steps. If we're running at 50 microseconds as a time step, we'll run for 50 seconds. Again, 1 million steps. That way we're comparing a one-to-one relationship. Now what this chart is showing is we have different configurations for different types, and we did it all in one CPU on the left side. So the black numbers represent the number of seconds it takes to do the total simulation in one process, or essentially the traditional way of running EMTDC. Then to the right, we use different protocols here. We use the InfiniBand or the shared memory model or the TCP, and we compare the performance numbers. Then we did it whether we're in the same computer, so all in one computer, or whether we're going across computers to use multiple computers to help with the problem. So we can see a whole different variety of numbers here, but essentially what you'll see is that I have colored in essentially black is more or less par, blue and green is better than par, and orange and red is less than par. And in a lot of the smaller cases you can see it's very clear that in almost all situations the TCP method is much worse, or just worse than the single CPU. It's only until the scale of the system grows to a significant size that the TCP is useful. Now if we look at shared memory, or we use the InfiniBand, we can see that even though we could be on, say, a single node or a single computer, if we go across nodes, even in a tiny situation like the simple AC, we still get relatively close to par performance across nodes or across hosts. So the communication impact is dramatically less using the high performance networking. If we continue to increase, we can see that both the shared memory model and the InfiniBand are very similar in performance numbers. So the InfiniBand essentially can be thought of as much like a shared memory model, but works across hosts, because the performance is very close to what we have implemented in terms of a shared memory model. So as I go down, we have a simple AC network, we have the secret benchmark DC link that I just showed in my presentation on PSCAD. Then we have a couple of wind park mixed models, and then we use some 39 bus to 118 bus. We go down further, we scale it up now. Now we can get to some real benefits. So we look at, say, a wind park using 10 machines, where all 10 machines are simulated on separate CPUs, and the main network is on an 11th CPU. We can see that the performance numbers in the all-in-one case start to really grow dramatically. So the all-in-one case in this 10 machine example is already at 679 seconds. But in the shared memory model on a single host, or using InfiniBand across hosts, we're at 117 and 130. So the performance is already significantly faster on even just 10 machines. We're already getting 5 times faster. If we go to a larger number of machines, say we go to 22 machines, now we're at a scale where it's getting harder to even fit on a single computer. We have over 1,000 seconds to run in one process, but using the shared memory model or the InfiniBand, we're between 160 and 214 seconds, which is still much better than the TCP, and certainly much better than the TCP across nodes. So we're still 5 times faster. We go to 38 machines, again we're at 1850 seconds, whereas shared memory and InfiniBand is at 250 to 270 seconds. Still much better. That acceleration is now, we're in the neighborhood of 6-7 times faster using a wind park with 38 machines. These machines are simulated in full detail, so you don't have the effects of aggregation on the models. Now if we go to a larger transmission network, we used a 2,500 bus transmission network, and we broke that transmission network into 40 processes. On a single process it took 18,000 seconds, which if you do the math, it's several hours to solve that. It's quite a long time. However, when we did it on InfiniBand and we did it on the shared memory model, we, interestingly enough, actually had a far better acceleration on InfiniBand than we did on shared memory. And that can be explained due to a number of things. And one of the big things is simply the congestion on a single machine, and the operating system creates a big impact on performance. So let's have a look at what happens when we take those 39 bus cases that we talked in the middle and really push it to the extreme. So these two lines are really interesting because what they represent is if we increase from a single 39 bus to 40 39 buses all ringed together on a single machine versus what happens if we run using across nodes using InfiniBand. What's interesting to note is that these machines are 20 real cores which hyperthread to 40 logical cores. Now, as expected, when we get to 20 cores, the machine will have to use hyperthreading to be able to manage all those processes at the same time. What we expected and found is that the performance dropped off as soon as we got to 20 cores, and now we're running into logical cores and using hyperthreading. What is also interesting is that this effect actually comes into play at around 1516 processes on the computer. So this is a little bit of an unexplained region here. It might be due to the fact that the machine is starting to become congested. It may also be that the operating system is starting to use hyperthreading. It's unclear exactly why we see this blip before 20 CPUs. But you can see at 20 CPUs, it's exactly into the hyperthreading band, and before 15, it is quite optimally loaded such that it's getting maximum performance. So this quickly tells us that while you can use a machine that's hyperthreaded to 40 CPUs, you have to expect that if you're using more than the number of physical cores, you're going to get a detriment in performance. In this case, about a 70% drop off in overall performance. On the upside, at least you can run it. You can run 30 processes on a hyperthreaded machine using this technique, but you can't do that if you don't have 30 logical cores. This way you get more cores, you just have to sacrifice performance. Now if we look at the across node, this yellow line here, you can see how beautifully flat and smooth this across node performance is. And that's because we're using InfiniBand, we're using two 40-core machines, and we're loading those machines evenly across. So neither of those machines is exceeding the amount of cores they have available. And in fact, sorry, I should correct myself, there's actually more than 40 here. So this is probably very likely more than two machines. It may be upwards of 3 or 4 machines. But any way you look at it, what it does show is that if you have the CPUs available and you have the networking across it, you can distribute the load evenly and get excellent performance and excellent scalability. So that's what this graph shows us. Now, as I come kind of down to the conclusion of this, we find that what we have here is a map of our 40-way split. The circles represent individual processes. The colors of the circle represent groupings of processes based on their connections. So the circle in the middle is PSCAD itself. The red lines represent the communications between PSCAD and each of the EMTDCs collecting data. They're fairly low bandwidth, so they're not critical to the performance. However, the other lines here, the green lines, these are the individual communication pathways between the individual subsystems in the EMTDCs. So essentially, these green lines represent one or more transmission lines connected between the subnetworks. The problem becomes it's increasingly complicated as you scale it up to determine how to split this effectively and get optimal performance. And this is where we are running into some new frontiers of figuring out how to deal with this kind of problem, which is starting to look more and more like a graph theory problem. We used a simple chain clustering algorithm here to demonstrate how they're split into groupings, but it's unclear at this point exactly how to break large systems into many, many CPUs. If we stress test it further, here's the ultimate. This is the stress test where we ran on our 160 logical CPUs using InfiniBand. We stress tested 150 EMTDCs with about 12 connections per EMTDC to every other EMTDC. The end result is we have about 1,500 or more communication pathways. This is where we find that the hardware reaches some of its limits. This is encouraging though, because this is a very, very large number of communication pathways, and it will be a long time before we reach that point that we need that many. So it does demonstrate to us that the hardware is more than capable of dealing with our future goals, at least in the next foreseeable future. So we have a mesh configuration. We reduce the computational burden per process. We are optimally mapping large numbers and broken apart into subnetworks. Now we need to look at intelligent graph theory methods that may be required to optimize loading on processors and optimizing the use of processors. And that concludes pretty much what I wanted to tell you today. So what are the conclusions? Well, the communication fabric has overcome some of the conventional limits of scaling with TCP/IP. You have no mutexes involved. There are no semaphores in the shared memory model, creating exceptionally low latency. The InfiniBand offers the same performance. We have not yet used processor affinity, but by using non-blocking methods, we've been able to encourage the operating system to keep all the processes in context, and therefore they remain solving at maximum performance. Separating the communication fabric from EMTDC itself improves portability. We have also built a co-simulation interface using the fabric that just requires matching message protocols between each side. And so you can simulate between EMTDC and some other program, whatever that may be, even a mechanical model, for example, of a wind turbine. Also, subsynchronous interactions are now more possible to study because we have full fidelity. And thank you very much. At this point, I'll take any questions. I think George will be answering some questions if you have any. And I thank you for listening.